Okay, thank you very much for this opportunity to talk here. We did also some light scattering experiments and modeling, but today I will be talking about atmospheric phenomena. We did some studies also about atmospheric halos, but today I will be talking about a topic which is most close to my heart. This is meteor phenomena in the atmosphere. And I tried not to make it too heavy on the formulas. So if anyone has questions, you could always reach me. I think most of you have my emails and contact details. So why this is interesting, I'll give just a few perspectives. You can see here that we have a lot of fireball networks worldwide. This is roughly how a modern image of meteor detection looks like. And I mean, 100,000 is just a very modest estimate. I think we have much more meteor registrations to date, today every year. And also, if you go to meteorite collections in the museums worldwide, you would also see that we have actually about 100,000 meteorites already, close to this, because many or some are not registered yet. However, if you want to have a meteorite, which is a piece of space rock in your hands, available for laboratory studies, and you also want to have a trajectory and understand where the object came from, when we only have less than 50 cases until now, which I was just wondering if I could get, we probably see it too, right? Yes, so we have less than 50 cases, which kind of where we know where meteorite came from. And it's simply a little bit of more persistent analysis and a little bit of more robust observations to be done to vastly improve the statistics. This is, I find it very intriguing, because this is basically a way to get free samples to our hands. And I'll briefly give some definitions, which I'll be using. So a meteoroid is a solid object which moves in interplanetary space, and it can be anything smaller than asteroid and larger than an atom. So it can be a very tiny dust particle released by a comet, for example. When this meteoroid comes to the planetary atmosphere, it interacts with the air and it produces a visible path, which we call a meteor. If meteor is of essential brightness, we would sometimes refer to it as a fireball or bolide. And finally, only a tiny fraction of these objects make it through the atmosphere, land on the surface, and could be recovered in form of meteorites. So this is how the process looks like. So the object comes from the trajectory, from its orbit, it comes to the atmosphere, it experiences preheating, and at some point it produces light. So we can sense the luminous trajectory. And the most prominent physical processes which occur are light emission, mass loss, so the object ablates and loses mass, deceleration, it starts to decelerate. And it also forms a fusion crust. For this meteorite which would be recovered, you would often see this dark fusion crust on top. It also experiences oftentimes fragmentation, which is producing a fragment or even meteoritic dust. And we also have interplanetary dust or micrometeorites phenomena, which are appearing on the less common scale, on the less scale of sizes. And at some point, the object would terminate the light of a luminous trajectory, which would basically be because kinetic energy is not sufficient to produce a light at this point, which could happen in two cases. First case, where object simply is too small, so it completely vanished. The mass is too small, so it doesn't have sufficient kinetic energy. However, the second possibility is that there is still considerable mass to be recovered, but the velocity is too small, so that kinetic energy is small to produce luminosity. And in these cases, this is where we call called dark flight trajectory could be calculated, and meteorites could be recovered on the ground. This is what we call a strewn field, because usually we have a number of meteorites to be recovered, and this is where we account for winds and other like more terrestrial events. There are a lot of ways to detect meteors. Here I list some. Now also space-based observations and airborne observations come to play in more recent years. So we have more and more data available for analysis. And this is what comes to like recent observations of meteors. But if you go to the past, to the like geological past of our planet, you will see that eventually on a larger time scale, you could see much larger like impacts. And this is example of largest verified impact crater on Earth. It's called Rutherford in South Africa. And the radius is about 300 kilometers. So eventually something really huge could come and produce a huge event. And when we have a little bit differently scaled impact, so this is Barringer, crater Barringer in Arizona. So this is about 1.2 kilometers in diameter, but it's very nice singular structure, and you could see very easy it in satellite images everywhere. And also Lonar Lake is quite similar structure. It's lake inside, it's in India, but I find these two quite similar. So as you would see, sorry, as you would see later, there is actually explanation. So for physical parameters, why certain events produce this kind of singular big craters on Earth. It's kind of, they could be grouped in a sense. And the other group could be, for example, seen with the example of Sikhote-Alin, which happened in Russia, meteorite fall in 1947. So it produced a lots of fragments, iron fragments in this case, and a lot of impact craters. And then there are also cases like Tunguska. So some large objects come to the atmosphere, it produces huge shock wave. It nearly reaches the surface. It produces huge damage, like forest was demolished in the large area. But when it has no meteorites, no craters. So this all could be explained with modern techniques. This is how Tunguska looks nowadays. So the area was damaged over 200 kilometers, and it's over 100 years now since Tunguska, but you could still see where it happened. And if it would not happen in remote forest areas, so it could easily destroy a big city like Moscow, here is an example. Another reason, of course, why I think this is interesting, the meteorites were basically pieces, samples of comets and asteroids. And they literally could help us to reveal the history of the solar system or planetary systems in general. One possibility is to organize a space mission to go and try to recover a sample from an asteroid or comet. So example could be Rosetta going to comet Churyumov-Gerasimenko with the hope to recover some sample. So it costs billions of euros, and the result is not certain. And here we have basically same thing going other way around. So the difference is that we are not choosing a sample is choosing us. And we could do the whole thing for free, literally. So we could just go get observations, calculate where it lands, go pick up a sample, and here it is. So the freshly recovered sample in the lab. So for me, it's a cheap, almost free, complementary approach for expensive sample return missions, which are now organized by space agencies. And because this is so interesting, so people usually organize so-called multi-station observations, and they allow us to calculate, for example, height, length along trajectory, meteor intensity, which is how bright it was, spectrum, polarization, anything you could come up with. And first attempt was done in Harvard by famous astronomer Fred Whipple in 1936. So it was lasting until 51. They collected a lot of data, a lot of orbits. I think, I know no meteorites were recovered, at least not that it would be documented. And the next was Andreev Observatory in Czechoslovakia at the time. And they started in 51, and in April 7, 59, they photographed the first fireball, which produced a meteorite, which we recovered. So this was the historical image of the first fireball that they detected. And using this trajectory recorded, the place of meteorite position was calculated, and 4 meteorite fragments were recovered of Shibram meteorite. So since then, as I mentioned in the beginning, we have around 40 cases of various meteorites recovered with orbits. And this is example of Neuschwanstein and Innisfree. And usually what we are interested most is how bright was event. So usually some people use brightness for more detailed studies. You could use brightness, for example, to decide if object was oriented during its flight or it was trembling. You could also use brightness to infer about fragmentation points. But the most important is height and velocity, because based on rate and height, you could actually say a lot about initial mass and also the way the mass was lost with the time during the trajectory. In Finland, as also in many other places, we have Finnish fireball network, mostly run by amateur, amazing work, truly. Like we have very strong team, and some people are very motivated. For example, Esko Luutinen was with us, was leading the effort, and he just did tremendous job, very incredible results. And I'll probably show with one example what we recovered. Like one of those 40 meteorites what we recovered was registered in April 2014. And this is the nice image of a fireball. It was actually a really nice story behind this. There was a school teacher who wanted to join the network just for, as a hobby. And this was first night of his observation, so he got this incredible image, which led to meteorite recovery, among other things. We registered the fireball from 3 Finnish fireball networks sites, but we were still a little bit short of observations because, like some images were just as poor as this, so it was only more or less used for timing of the event. And we were able to just find a video in the internet, which was done from Russian side, from Snezhnogorsk, and using these 3 observations from Finland and 1 video we got from Russia, we were able to reconstruct the trajectory and calculate the impact point. So this is the video what we got. I don't know, let's see if it will run. I think like now some years has passed since this event, but I find it still incredible that we were just able to find some random video more or less in the YouTube. We were able to actually understand where it is, to locate the car, to account for the speed of the car, to get the reconstructed trajectory, to get all the perspectives like of image with account for buildings and everything, to find Jupiter on the sky, and to get precision to such point that actually I was able to send an expedition from Ural Federal University and Helsinki University, which would be able to recover a meteorite in 2 days. I think it's incredible result, really. So this is the visualization of a trajectory which was done. You could see roughly where it was going. So this is Finland, this is Russia here, and this is where it landed. And for cases like this, we do a detailed dark flight simulation using DFMC model, which I referred to above. in the presentation. And this is what the model produced. And here in the square, we have a zoom in. So in this area, we actually have these two pieces recovered, 120 grams and 40 grams. And you could see that it matches incredibly well to what the model has predicted. This is Nikolai Kruglikov, who recovered the first meteorite sample. So this was the second day of third. And he just spotted it actually literally from the car, but was extremely lucky. And when the sample was very fresh at the time of recovery, so it was immediately analyzed, and we could infer a lot about history of this object when we have the piece in hand. So now, just like to sum up this, I will also tell you what we generically can do to understand the impact. So with larger scale events, what I showed you in the beginning of the presentation, I'll show you how to explain actually what's happening. So these are like 3 historical events which I showed you before. With Canyon Diablo meteorite, which is the one causing the Barringer crater in Arizona, Tunguska-like impact, Cihotealine. So these are 3 different categories, so to speak. And then those meteorites, which are like more small scale impacts of more kind of adequate size, and which are happening much more often. So we actually could classify them using the 2 parameters, which are alpha and beta here. And I'll explain what these 2 mean, because I think this is really important. So the ballistic coefficient alpha, so this is the definition of it, and you could find it in lots of papers by now. If you look into what's here, so this is like density of air, height of homogeneous atmosphere, cross-section area of the meteoroid at the entry to the atmosphere, divided by initial mass of the object, sinus of the slope, and so this would be like a ratio between masses in air in front of the body to initial mass. So it's like a ratio of masses. And similarly, mass loss parameter beta shows the ratio of kinetic energies. So we don't look how big the kinetic energy was of the object when it comes to the atmosphere, but we look what it is compared to how much energy you need to apply to fully destroy the object in the atmosphere. So this is where difference come if this is made of iron or made of ice. And here also, like, we don't look how big the object is, but how favorable are conditions that it actually reaches the ground. This is, for example, where slope of the trajectory is important, and shape is important. So now if we put these events on the logarithm alpha versus logarithm beta scale, which would mean that this, for example, area is where alpha and beta are too small, they're not negative, but just simply between 0 and 1, we could eventually place our events. So this would be the single crater, this would be many craters, many meteorites, and this would be Tunguska-like impact. And this would be like more common meteorites, so to speak. And we could eventually have a curve which would separate events which produce a crater. We would have a curve which would separate events which would produce a meteorite. And we would have events here above this line, which would be fully ablated. So even so, Tunguska, as you could see, had a very small alpha, so had a huge mass at start. It also had a large beta, which means that it simply couldn't produce a meteorite, no crater, because it was simply too fragile. So this is a simple way to classify. This is our ANAMA case, which I was showing you just before, the Finnish case. And this is where Chelyabinsk comes. I like where it comes, basically like an etalon, almost one-to-one. And we are collaborating with a lot of groups worldwide with this example of distant fireball network in Australia. So we run all this through all the fireball detections through this algorithm. And we detected that a few would produce a meteorite. And in this fireball network in Australia, it's very super easy to go find meteorite. Well, maybe not super easy, but much easier than in Finland to go and find a meteorite in this set. So we actually went, look for it, and it truly matches. So everything what's predicted to be a meteorite is a meteorite, which I find incredible. So these are conclusions. I think I need to plug my computer, but I'll be with you shortly.